Mr. the Chairman, I am pleased to present you my research work entitled Biocomposites based on poly-3-hydroxybutyrate co-3-hydroxyhexanoate chemically modified agave fibers. This work was carried out in the LMPA laboratory in collaboration with ERDL from the University of Bretagne Sud in France. Plastics materials from fossil sources have an important and pervasive role in our everyday life. However, most of these synthetic polymers withstand the ocean and terrestrial ecosystems for years, thus constituting a source of environmental pollution. The replacement of petroleum-based non-biodegradable plastics with alternative biodegradable biomaterials with comparable properties has become an industrial, social, and environmental priority. This is supported by the evolution of the world production capacities of bioplastics. 34% increase in this production is recorded between 2015 and 2021. Among the biodegradable polymers, PHBHHX, which belong to the family of hydroxyalkanoates, is a microbial biopolymer having excellent biocompatibility that makes it a potential candidate for substituting petroleum-derived polymers. Furthermore, PHBHHX has moderated percentage of crystallinity, melting temperature, and it is a soft material. The biocompatibility and biodegradability characteristics of PHBHHX make it an outstanding material with broad applications in a wide variety of sectors, such as biomaterial applications involving the fabrication of cardiovascular stents and medical packaging. PHBHHX can be also used in engineering applications for cosmetics, hygiene products, printed wearing board for electronics, and helmets for cyclists. However, despite the great expectation generated by PHBHHX, its use remains limited due to its high production cost. One of the most common approaches to reduce the cost of PHBHHX while keeping its functional properties is to combine it with abundant and cheap cellulosic fillers to produce biocomposites. The use of agave americana fibers in PHBHHX biocomposites is an interesting topic since the fibers are locally available, have low cost, good mechanical properties, and renewable resources. In this slide, I showed you how the agave americana fibers are extracted from the leaves. However, as well known, mixing PHBHHX, which is hydrophobic in nature, with agave americana fibers, which are hydrophilic in nature, results into non-compatible systems due to formation of fibrous aggregates. The weak adhesion at interface leads to poor mechanical properties and brittleness. It is necessary to carry out some chemical modification to improve the interfacial adhesion. Among the chemical modification methods proposed in literature, there is matrix functionalization or compatibilizer agent or fiber surface treatments. In our work, we choose alkaline treatments, saline treatment, and both alkaline-saline treatment. In this part, I will show you some results on chemical characterization by ATR-FTR of agave americana fibers before and after surface modification. Recorded in the hydroxy peroxide region, it is noticed that the absorption band intensity of hydroxyl groups significantly increases after combining alkaline and silanol treatment, resulting in formation of silanol groups. There is also the presence of shoulder at almost 769 cm-1 for silan and combined alkaline-silan fiber treatments due to the self-condensation of thymos in the fiber surface, leading to the formation of siloxane groups. In Figure 3, the DTG thermograms of agave americana fibers are presented before and after surface treatment. It is observed a significant peak at 295 degrees C in the untreated fiber curve attributed at hemicellulose, which disappears completely after alkaline treatment. There is also another mean peak corresponding to the decomposition of cellulose between 333 and 350 degrees C. Figure 4 shows the SEM micrographs of pH-BHHX biocomposites. In the figure relative to untreated biocomposites, there are aggregates with the presence of micropods on the surface indicating a weak interfacial adhesion. The next image corresponding to the alkaline treatment biocomposites, there is still microscopic pods indicating poor dispersion. In the silan treated biocomposites, it is observed better weightability of the fibers and also reduction in the number and size of aggregates. Finally, in the combined alkaline-silan treatment, it is observed a regular and homogeneous morphology indicating an improvement in the interfacial adhesion. The TGA-DTG thermograms of neat pH-BHHX and its biocomposites are shown in Figure 5. It is noted that there is one single mechanism of degradation for pH-BHHX, whereas for the biocomposites there is a second degradation step relative to the cellulose. Basically, it is noted for the alkaline biocomposites less stability and also alteration of the cellulosic structure. And finally, the other treatments are more efficient, indicating strong interactions. In Figure 6a, relative to the complex viscosity evolution, it is observed an increase in viscosity after treatment of the fiber, being more pronounced for the combined treatment, indicating restriction in chain mobility. In Figure 6b and c, relative to storage and loss modulus, it is noted an increase in these properties at low frequencies, meaning strong interactions between fibers and matrix and subsequently better dispersion state of the filler. These results are in agreement with the morphological data. With increasing angular frequency to almost 0.15 Hz, a pseudo-plateau is clearly noticeable in all biocomposite samples. This is attributed to the strong interfacial bonding occurring between the natural fibers and the polymer matrix. It can be concluded that the SEM micrographs have shown that the different chemical treatments of agave americana fibers lead to improvement of the dispersion of the fibers in PHBHHX matrix, however more pronounced for the combined alkaline and sealant treatments. Moreover, the combined alkaline and sealant treatment of the fibers is the most efficient one regarding the thermal and rheological results. And thank you for your attention.